Good morning, everybody. Our second test was a raging success, in my opinion. Everyone passed and did very well. Congratulations. If you haven't collected yours from the front of the room, please feel free to do so. Scores, very good. Everyone passed, and the average is a very high B that comes up to an A. So I'm very proud of all you guys. We'll spend a little bit of time talking about a couple of the commonalities, some common errors that I saw, and then we'll open up the floor to any questions that you guys have. First page, generally no issues. Just occasionally, just the thing about secant is it is the opposite of cosine. Meanwhile, cosecant is the opposite of sine. So it needed to be secant of theta equals 7.81 over 5, as opposed to over 6 or inverted. So secant is hypotenuse over adjacent. Second page, the isosceles triangle. Very good all around. Thing about isosceles triangles is the two bottom angles are both 70, the top angle is 40, but if you divide it into two right triangles, the top angle of the two right triangles would each be 20 to add up to 40. But no real issues with area and perimeter there. 5 and 6, occasionally some sig fig issues. There are 3 sig figs within this particular question. The 1.28 meters per second has the lowest number of sig figs, so we use that number moving forward. So the answer should be 0.0736 newtons. Now, for number 6, your answer to 6 did depend upon your answer to 5. So if for whatever reason your answer to 5 was not completely what I was expecting, I graded 6 on an individual basis based on what you got for 5. So if for 5 you got something completely wrong, but you used that number correctly in the next part, you got full credit. If that was the case, I put okay and then a check mark just to show that what you did for 6 is correct. It's just using the incorrect data from above. But it should have 3 sig figs too, and it should, using the correct values all the way through, be a very low percentage, less than 1%. 7 and 8 were very good. 9 was designed to be the longest one. I always put more than 100 points on these, and so one of those questions ends up being the longest one that has functionally the bonus points attached. 9 was the one that had the most work, the most steps, and was worth the most for a completely correct answer. The full picture should look something like this. We've got line A moving at 60 degrees. Then we have line B. To draw it right, you want to put a new coordinate system at the end of line A. And then we draw line B, which is 7 miles at 223 degrees. Starting from the x-axis, 223 degrees would go here. That would be about 43 degrees into the third quadrant. So line B would do this. It would be 223 degrees from the positive x-axis, which can be reinterpreted to mean 43 degrees from the negative x-axis, which is the number that I use on my key when doing all the trig. That means that the final answer, the actual vector sum of these two things, would look something like that. it would have a negative y component and a noticeably larger negative x component. And the final answer for the vector, for vector C, and all you needed to do the math part to completion is just tell me basically the coordinates of this spot. Adds up to negative 3.61 on the x-axis and negative 2.17 in the y-axis. There's a lot of individual parts to this, like drawing all the lines, doing each individual step of trig, adding together all of the trig functions that you found. So there's a lot of places for partial credit here. The only way to get nothing is to leave it blank. As long as you attempt it, you definitely got something. But the main goal is to first draw the picture, then divide each of the starting vectors up into its components, add the x's together, add the y's together, and that will give you this number. That is a terrible straight line. I have met physicists who are artists, but they are in the minority. This was the hardest, or at least most involved question on the test. So this is probably where most people probably lost some amount of points, but that's fine because that was baked into the question. That was the intention. This was meant to be the hard one. Number 10 was also probably on the trickier side, but there was fewer steps involved. I would like to at least show the math for 10 really quickly. The physical situation in 10, you have a rock on a cliff and it's going to drop straight down. This is essentially a projectile motion question, but we aren't throwing it, so it's not going to rise at all. It's not going to go horizontally. It's just falling straight down, only moving in one axis. That makes it one-dimensional, which makes it much easier to solve. Part A, we are asked the time it takes that rock to fall. The things that we know for certain are the height that it will fall. It's going to end up 100 meters beneath where it started, so I'm counting that as delta y and making it a negative number because we are descending. You don't have to make it a negative. I am doing that for my own internal consistency though. We are also told, since we are dropping the rock, this definition is hopefully consistent across the board. When I drop something, it starts stationary and then it is only accelerating due to gravity. So if the object is dropped, initial velocity should always be 0 meters per second. And because it is falling, we also know, falling on planet Earth, it will accelerate down at negative 9.81 meters per second squared. We know these three things. We want this one thing. There's only one formula that contains all of this. And that's of the Fantastic Four. That is formula 3. I'm going to reframe it in terms of y's instead of x's. This formula is used when an object is moving in a specific axis and accelerating in that axis as it moves. And that describes falling. We move downwards, we're accelerating downwards, and moving in that direction some distance as time passes. So this one formula contains all of those things together. And eventually, you know delta y, you know this is 0, you know ay. We just need to solve for t. I made both of these numbers negative, and they will both cancel, like the negatives will cancel. It would also work if you made them both positive. If you set up your system like that, that's fine. You just need to decide if down is negative or not and stick with it throughout the whole thing. negative 100 equals, this whole term falls away to 0 because BIY is 0. 1/2 negative 9.8 t squared. Solve for t, and we get 4.52 seconds. We then need to use that information in the next part of the question, and, well, there's actually ways to do part B that don't necessarily involve that number, but, again, in the interest of fairness, if you did this and for some reason this number was incorrect, and you then used this number in part B, I didn't automatically mark part B wrong because the number was going to be wrong. I marked it as correct as long as you did the correct steps with whatever number you got here. Part B, I find the simplest way to do part B because we are asked for simply the final velocity before impact. We know time falling, we know acceleration, we know initial velocity. I find the simplest way to do that is A equals delta V over delta T. Negative 9.81 equals VF minus V initial over 4.52 seconds. VF should be negative 44.27 meters per second downwards. And in the past, I've had some students raise an eyebrow when I ask final speed at the ground because, once it hits the ground, it should stop. So I tried, if my wording in trying to describe max speed right before impact was confusing, please let me know. I'm trying to make sure that the phrasing is as convenient for students as possible. This would be the speed at which it goes splat. So this would hurt. This is faster than I think most human pitch is.
And when I use the other equation, I got the same thing, but it's positive.
Well, the negative just says down, really. Other formula, do you mean?
The B final squared.
Yes. So often in physics, there is more than one way to do the same thing. Formula 4 would accomplish the same thing. Fantastic Four, Formula 4. We want final velocity. We know this is 0. We know what acceleration is. We know the displacement we are going to travel. Actually, if you plug in two negative numbers here, you get a positive answer out. Either method works.
Say the positive and the negative, it doesn't really, are you going to count off for that in the future?
In the future, direction is very important because to give a full, complete vector answer, you need both the number, the unit, and the direction. Now,
if it's positive, we just put south behind it.
Yeah, south or down, any descriptor really. When I'm say grading on a test, I consider the direction to be kind of like a unit. And when I'm grading the question, I'm looking mostly for, did you write down the formulas? Did you do most of the algebra? Did you get to an answer? You can get most, if not all, of the credit on a question just by those steps alone, the way that I grade. On the answer, if it's say a 10-point question, if you leave off a unit and you leave off a direction, you might lose a point out of 10. Just to give you a frame of reference for importance. It's there, you should have it, but it won't be the end of the world if you forget. Overall, very good test. Well done, everybody. I feel like we're in a good position to move into finals period. Do you guys have any questions, and how do you feel?
It's the best way to study for our final just to look at the past two tests.
Excellent question. That is one thing to do, yes. My intention is to upload to Brightspace, similar to the last several tests, a list of all the topics that will be present, and some practice questions that will be optional but will be good practice. They're not up yet. I still need to make them because I have to make the exam so I know what's on it, and then I have to pick questions that are similar but not identical. So there's a chain of events I have to get through. But by next Wednesday, because that is the last day I will see you guys for normal class period, by next Wednesday, all of that review material will be uploaded for you to use. Gesundheit, whoever else sneezed as well. I know I missed one. All that will be uploaded. We can spend Wednesday looking over it, making sure everyone's clear on what will be there and what won't be there, what all the equations mean, etc. And I think this one equation sheet from the last test should be all you need for the exam as well. If I need to add something to it, I will revise it and let you know and make sure you have an updated copy. But this should be it. And at least one more thing you can do to study is just look at this and make sure you know what all of it means. You will have this piece of paper. You don't have to memorize it, but you need to at least know how to use all of it. So looking at old tests is good, looking at old homeworks is good, but I have, over my brief career as a teacher, and we started 5 years ago, in that time, one of my most frequently asked questions is, can I have more practice problems because just looking at old homework doesn't help me? I need more things to do, which is why I try to have the practice guides up. So those will be available soon. Wednesday, we will go over any and all of that information. Additionally, kind of a non sequitur here, I usually end winter semester by bringing in Christmas fudge. But winter semester didn't end with Christmas, it ended with Thanksgiving. So I didn't get to do that last semester, which made me sad. I kind of just want to bring in my grandma fudge the fudge that I normally make at Christmas. It's grandmama's recipe and I love sharing it. Would anyone complain if fudge were here on Wednesday? Okay. Does anyone not eat chocolate? I have to ask. Usually when I bring in candy, there's someone who would prefer fruit. I'm probably going to bring in Rice Krispies and Doritos just in case. It's been a kooky year and a kooky planet, and I just want to have something nice. Because I enjoy and appreciate you guys, and I want to make sure we end on a nice note before I see most, if not all of you, again in the fall. So, keep an eye on Brightspace for exam stuff. Does anyone have any questions right now about the test or upcoming? Yes?
So the format is pretty much the same for the final as what we've been doing?
Yep, just longer. Think of it as both tests combined. That's basically it.
So no Newton's law of projectile motion?
This kind of projectile motion would be there. I don't feel comfortable, I don't feel we've worked enough examples in proper class hours to put in a full range equation just yet. I might ask something about it, like conceptually, does the movement in the y-axis directly affect the x-axis? Answer no. So maybe some concept questions, but I tend to err on the side of making sure you've seen the content and are familiar with it before I grade you on it. So, a little bit of housekeeping. That last question from the homework, from homework 7, that I had you tear off the back. I was not worried about that one. I removed it so that I'd make sure we'd have the homework done in time for me to grade it and get it back to you. That particular question is just dead. It's gone. Don't worry about that one. However, I would like to spend the rest of today looking at these questions, the homework 8 Newton's laws stuff, because Newton's laws is peak foundational physics is very important, and I did not create this particular class of physics. I did not create Physics 2000, Physics 1400, whatever you want to call it. Dr. Odecore invented the idea of this class. There was a list of things that he wanted to make sure that the students saw before Physics 1500. Among that list was Newton's laws. But semesters being what they are, and time crunches being everything right now, they didn't always come up. There wasn't always time to cover them in the proper semester. So I would like to at least discuss these with you guys. They might not be, there won't be any math about them on the exam, but I would like to do these with you right now to get the information in your head so it can percolate until fall.
So should we be able to round them out on them?
Usually on tests, I will list the laws and ask you to number them. Like, you will be given the statements and you just have to decide which one's first, second, and third. Because memorizing is hard and I can't remember my own formulas half the time. So we are going to do these together just as a practice or concept exercise. Let me pull up my 1500 notes. Shut up, Cortana. Where are all my files? There we go. Okay. So, Newton's laws. Very important because for hundreds of years, physicists used Newton's laws to explain pretty much everything, at least in terms of the physical universe that we inhabit. The laws themselves are famously 1 through 3. The first law, you've interacted with all of these before. You've probably heard them summarized. This is not new information, it's just this is them in the context of Newton's laws and which one is numbered which. Law number 1 says that an object at rest or an object in constant motion will remain in that constant motion, be it moving or not. It will remain that way until acted upon by an outside force. You can begin copying at your leisure. This law is called the law of inertia because this law is the definition of the term inertia. That is how that word is spelled. Did anyone here ever watch the 90s Bill Nye show? Remember in the theme song, like one of that background voice would chime in with random facts. Inertia is a property of matter. I'm literally inertia, a property of matter, which compels it to remain in its current state of motion. All matter wants to keep doing whatever it is doing. It is an object's tendency to just chill. Whatever it's doing, it's easiest to just stay that way. This is most clearly evidenced in the fact that all of the objects sitting on my desk will just stay there until I, an outside force, do something about it. The inertia of the objects says, yo, stay that way. This is true of stationary objects. It is also true of objects moving at constant velocity. The classical example of this is something flying through space. Because in space, there's really no functional outside forces on the object, so an object that is just free flying through the void will continue moving at the same velocity until something stops it, until it hits a planet or something hits it. So, regardless of what type of constant motion you have, whether or not that constant motion is constantly zero or constantly something else, objects tend to stay that way until you literally push them and force them to change. And that is the summary of first law. Questions so far? Second law is the easiest to summarize because it's literally just an equation. Because in physics, physics as a, I almost said the word art, physics as a discipline is all about taking the universe and turning it into equations. So we reduced all of Newton's second law down into just those three variables. What this law says is, if you exert a force on a mass, it will accelerate. To make anything change its motion, to make something accelerate, you have to push it. That's all it says. If you want to make something accelerate more, you have to push it harder. And the mass of an object will determine how much it responds to any given force. Pushing on a bowling ball, if I push with 10 pounds of force on a bowling ball, it will accelerate faster than if I push with the same 10 pounds of force on a boulder. Boulder has more mass, it will not accelerate as much with the same force. Good so far? Okay. Let's see. There's the three variables and then one below. So the three variables are, F is for force. We measure force in newtons. Yes, named after him. 1 Newton is defined as the force needed to push a 1 kilogram object and make it accelerate at a rate of 1 meter per second squared. It is the base unit for force, and you will never escape it because force will be in every physics class you ever take. In American standard imperial units, we tend to use pounds as a unit of force because technically gravity is a force, so your weight is a force. So you can use pounds to measure things other than just the force which gravity pulls on things. I think most pitchers and most boxers have their swings rated in pounds of force, if you actually go into the medical science of those sports. I did Taekwondo as a kid from about age 10 till I finished high school. And I learned this from him before I learned it officially from my science teachers. And my instructor. And he always framed it as, if you want to punch harder, you either need a bigger fist or you need to move your fist faster. So, force measured in newtons, mass measured in kilograms. I've mentioned this once or twice. Grams is technically the metric base unit, but all of our formulas from now till the end of your physics career should be using kilograms. They're scaled to kilograms. Because if we use grams, all of our numbers would be 1,000 times bigger. And that both scares people and is inconvenient because mass is in most formulas. Lastly, A is just acceleration measured in meters per second squared. Newton's third law is arguably the weirdest one, or at least the most confusing when you start thinking about it. You've probably heard the colloquialism, for every action, there is an equal and opposite reaction. The official definition adds a few more words. For every action force, there is an equal and opposite reaction force. I'm going to start listing some action-reaction force pairings as examples. In terms of forces, how would you describe what I'm doing right now? I am pushing against the wall. So, if I didn't write it out. If I push on wall, then the wall will push on me. You know what? I need to be a little more specific. Push into the wall. The wall will push outward on me. So this is our full Newton's third law statement. The action, I push into wall. The reaction, wall pushes on me. These are all if-then statements, kind of like computer coding. Whenever one thing pushes on a second thing, the second thing will push back. That is what this law says. That is, as we understand it, a universal fundamental constant. The details come in figuring out the objects in question and the actual forces involved in the specific interaction. If I push into the wall, then me, the professor, is object or entity A. This is the force into the wall, and the wall is object B. The action is always A pushing on B. The reaction, by definition of it being reaction, has to be B pushing in the opposite direction on A. It takes the form of, if A acts on B, then B will act in the opposite direction, but same magnitude on A. And I'm going into detail on this because the last question on that document you're working on is one of the biggest sticking points of when teaching Newton's laws foundationally to anyone, really. It took me a while to wrap my head around it. For every force, there will be a reaction force. That's a guarantee. If I punch the wall will exert a force back on my fist. Which one of those two things breaks depends on the structure of the object. Don't punch walls. But if I punch 10 newtons against the wall will exert 10 newtons back on my hand. Whichever object breaks is just the object that couldn't stand 10 newtons of force. List some examples of action-reaction pairs. So number 5 is asking for examples. There's one of them. Another example, punching the wall. Please don't do that. An example I like to use is a rocket ship. When the rocket blasts ignites the fuel and blasts it out of the back, the ship is pushing the fuel out of itself. Meanwhile, the fuel, like the vapor form, the actual explosion, pushes in the opposite direction on the ship. So that's why those propulsion systems work. Now number 6 on this actual document asks about a very specific case of interactions. Right now, you in all of your chairs are subject to several forces at once. We're still on planet Earth, so gravity is pulling down on you. That's a pretty universal constant as long as you are on this planet. So, gravity pulls down on me. That's sort of the initiating action. Gravity, that's the action. Gravity exists, it's going to be here. Now, the reason you're not falling to the floor at the moment is because you are all sitting in chairs. And those chairs are exerting a force upwards to counteract the force of gravity pulling you downwards. As long as the forces acting on an object add up to zero, it's as if those forces weren't there. So right now, all the forces on you are balanced, they add up to zero, and you don't accelerate from your spot. So at a first glance, it's easy to think, okay, if gravity pulls down on me, then chair pushes up on me. Do those make sense as an action-reaction pair? I'm getting some mixed results. That proves that you are thinking about it. The one part of this that actually does match a standard action-reaction pair is the fact that the forces point in opposite directions. That's cohesive. Gravity pulls down, chair pushes up. But gravity is the Earth acting on you. The force of gravity is literally the mass of the Earth pulling on the mass of your body. So the object acting here is actually planet Earth, and Earth is then object A. You is therefore object B. I guess me, I wrote me. I am object B in this scenario. The chair is not the Earth or me. It's a third object in this weird situation. So, and then we're back to me. So whereas a real action-reaction pair is if A on B, then B on A, this is if A on B, then C on B. This situation is not an action-reaction pair. This is a coincidence. If you are successfully sitting in a chair and it doesn't break beneath you, that's not an action-reaction pair. That's just, it happens to be that these two forces are acting on you are equal and opposite. One does not directly cause the other. The actual action-reaction pair is, if Earth pulls on me, then I pull upwards on the Earth, because all matter has a gravitational field, including, humans. We all have gravity. It's just very weak because we don't have the mass of a planet. But technically speaking, on planet Hoth, the Earth has a weight. It's a weird way to think about it, but we could think about it as I'm the planet and Earth lives on my surface. And that would be the reaction to this first line. If Earth pulls on me, then I pull on Earth. The second part, chair pushes on me because I push into chair. Granted, the reason we push into chair is because of gravity, but the chair doesn't care why we're pushing into it. It just notices human push on me, I push on human. As much as an object can think. Please list at least one reason below why gravity and normal force are not action-reaction pairs. They do not follow the typical pattern of if A on B, then B on A. Additionally, one other reason, action-reaction pairs cannot act on the same object. Notice the A and B swap here. The objects being acted on are different each time. In this false one written here, the objects being acted on are the same thing. So that's at least two reasons why these are not actually an official pair. And that's, like, when talking about Newton's laws, that is easily the sticking point that gets people the most, which is why I wanted to at least present it to you now. Because I think the only way it sinks in is with time and constant repetition. So at least you have the summer of time for it to sink in. Any questions about anything at all? Okay. With that, I believe that's all the information needed to have filled all of these in. This is mostly just a way of getting you the information and having you write it in your own hand, because in my own experience, things sink in better if I write it down and repeat it out loud. That's how I learn things. So make sure I have that by the end of the day. Since we did it together, it's basically just proof that you were here and that you learned the information. And with that, and having discussed the exam info, that's pretty much it until I think next Wednesday. Again, I will have the review information and study information for the exam uploaded to Brightspace shortly. At the very latest, it will be before we meet next Wednesday. And we will spend Wednesday hopefully enjoying some nice snacks and also making sure everyone is comfortable with all the information that will be in the exam. So, any questions at all about anything at all? I know I asked that repeatedly. It's probably an insecurity quirk of mine. Yes.
I have a question about 1500.
Mm-hmm.
Will it be outside again?
I'm teaching it, so no. I find that indoors, where you have a desk to space out your work and use a calculator successfully, and where I have this so that I can present to you notes that aren't written in my terrible handwriting, works best.
It was so distracting, like the bugs would come down, and there'd be like spiders coming from the trees.
Yeah, in the wind, like
Yeah,
in fall
it got-
semester,
it
you're
got
dealing with
cold.
things getting colder.
It
In
got
spring
so
semester,
cold.
you're dealing with all the wonderful details of spring.
Well, I dropped before it got too cold. It was cold. I had it drop in like October.
When I was a student, I don't notice it as much these days. There was a whole lot of inchworms in the spring here.
And they would come down from the trees.
Correct. I have not seen as many of them, but since I'm not living on campus, there's fewer chances for me to be affected by them.
Why can't I the worms out? I remember I was sitting there like the spiders would come down. It was so bad.
I'm
I
arachnophobia.
started picking the grass.
No spoilers, please. You have a good day, everyone, and thank you all.
You too.